So basically, iteration of reflections correspond to this recursive definition, so that alpha time iteration of reflection along COT is a theory that is T plus reflection append reflection for shorter iterations. Okay, so and basically, so in order to make it formal, one could define this. So Turing machine enumerating this axioms of series by recursion theorem, or one could do it via fixed point theorem. So basically, some machinery of recursive definition of functions of formulas is necessary here. Okay, yeah. So, but basically, so the general idea is that we iterate this reflection along an ordinal notation system. Okay, so then if one takes the say usual kind of ordinal notation system, or just some ordinal notation system that contains omega compensation function, then it's possible to formulate the following Schmerl formula that connects iterations of stronger reflection over shorter ordinals with iterations of weaker reflection over longer ordinals. So namely, here happens the following. So if you have iterations of pi n plus m reflection along some ordinal alpha, then the theory will be pi n conservative over iteration of pi n reflection along the ordinal omega m alpha. So basically, we put m many omega exponentiations below the ordinal alpha. So basically, so we're trading of one level of this arithmetical hierarchy in the reflection with one omega exponentiation. But of course, so the theory in this equation, the theory to the left is actually stronger than the theory to the right. Namely, so it has the same pi n consequences, but it have more consequences on the stronger levels. So pi n plus 1 and so on. Okay. And so basically, basically it's what Schmerl have found, and then it's possible to use this for the purposes of proof-theoretic analysis. Namely, say one could express series I sigma n as iteration of reflection, namely as just one time iterated pi n plus 2 reflection. So basically I sigma n is the same as one time iterated pi n plus 2 reflection. And thus it's possible to apply this formula and characterize pi m consequences of series I sigma n in terms of this omega exponentiation. It's possible to do the same for PA, but now we will get this just epsilon 0 iteration of reflection for every complexity level. Okay, so basically, then from this formula, it's possible to obtain various kinds of ordinal analysis results. For example, I think the most natural one for obtaining that's possible. The most natural one notion of proof-theoretic ordinals that is possible to recover from this analysis is notion of pi2 or proof-theoretic ordinals. So, namely, the class of probably total computable functions. So the usual way to define pi2 ordinal is the following. So basically, we can see that this fast-growing hierarchy, also known as extended Grigorchik hierarchy, for given ordinal notation system. So it provides us this classes of fast-growing functions, fast-growing computable functions indexed by ordinals, and then we want to associate a given theory with a particular ordinal such that so the probable total functions, probable total computable functions of the theory should coincide with this corresponding level of fast-growing hierarchy. And basically, the point now is that alpha time iterated reflection. So this probable total computable functions of alpha time iterated Π2 reflection over theory A are precisely 2 plus alpha level of fast-growing hierarchy. And basically, this gives, and basically, so this is really easy factor proof. So I think it's yeah, I think this observation have been done by Lev, so that it's possible to do it this way. And yeah, and so then just one just need to apply the required Schmerl formula and obtain characterization of Π2 consecutive theory in terms of this iterated reflection, and this will give you characterization of probable total computable functions. Okay. But also, so it's possible to extract other notions of proof-theoretic ordinals from this. For example, one could connect this iteration of reflection with transfinite induction, and thus characterize the amount of probable transfinite induction. And so this actually it's possible to but a slight modification of this argument is possible to obtain what's known as Π11 proof-theoretic ordinals. So this the upper bar, so the supreme of order types of probably well-ordered primitive recursive binary relations. So basically, so this is so the Schmerl kind formals actually are a very powerful way of proof-theoretic analysis in the sense that they allows uniformly to obtain various kinds of proof-theoretic ordinal analysis results. Okay, so yeah, so but so go to this situation with reflection in second order arithmetic. Okay. So consider so okay, as usual, language of second order arithmetic extends the language of first order arithmetic by additional source of variables. So now we have so in addition to usual first order variables that such that the intended range is the set of natural numbers, we have additional sort of variables such that the intended range are sets of natural numbers. Okay. So, and we, of course, we add membership predicate to the language. So we have this natural complexity classes for formula. So, okay. So basically, so we have this classes Π1n, so where Π10 is just the class of all arithmetical formulas. So formulas without second order quantifiers, we actually allow second order parameters, and so classes Π1 n plus 1 and sigma 1 n plus 1 are so are just this formulas with say with second order quantifier premixes followed by Π10 formula, so for formula without second order quantifiers. Okay, so this is basically the usual definitions of classes of formulas in second order arithmetic. So yeah. Okay. So our base system of second order arithmetic will be a system of arithmetical comprehension. So this so the arithmetical comprehension is this system second order arithmetic where the main axiom is the scheme of arithmetical comprehension. So the scheme that states that every set of natural numbers defined by the formula without second order quantifiers actually is a set. So for any for any property of of this sort, we could form a set. And it's well known that system AC0 is first order conservative over P. Okay, yeah. So yeah, so this is basically our setting. Now, so in the setting of first order arithmetic, we had these iterations of So we had this reflection principles that took into account this first order parameters. So basically, what if we go back, so if we look at this scheme of pi n reflection, here we need to actually to quite so also it was scheme, and so this and so it can range it over all pi n formula, but it was essential that it ranged it over formulas, not over sentences. So it was essential that we actually can. So we had this form that for set of possible parameters. If a particular example of a formula is provable, then it holds. So and so this, if you would formulate it without so just for sentences, it would be what the scheme that's known as the scheme of local reflection, it's behave considerably different way than the scheme of global reflection. So it's essential for us to also consider parameters in a second order setting, and it's a bit more complicated because, of course, in the first order setting, so you could it was possible to substitute parameters just by putting numerals in the formula. So in order to say consider the formula, say phi of 5, you just say something like consider formula phi of successor function iterated five times of 0, and it's basically your substitution of parameter. And this couldn't be done in the setting of second order arithmetic because so there are no some canonical term representing any given set, of course. So we need to make some adjustments for this. So now, so we still want to have this reflections to take second order parameters into account, but we need so we need to put some additional work into this. So namely, we will get around this issue, but by considering a language boldface L2 that extends the usual language of second order arithmetic by constants for each individual set. So in sense, basically it's this uncountable language, and when we will formally work inside second order arithmetic, it's basically this class size language. So it's yeah. So basically, in the setting of second order arithmetic, this formulas in this boldface L2 language will be cornered by sets. So because basically the formula in this boldface L2 language is a function. It's just first order formula, and then this bunch of set parameters that put inside it. So it's basically that. Okay, yeah. So I'll just continue then. So of course, so then we just have the usual classes pi1 boldface pi1n and boldface sigma 1n. So it's, this of course very much in line with this style of notations that is used in descriptive set theory. So when you have light phase pi1n sets and bold phase pi1n sets, where the distinction is that light phase pi1n sets do not contain parameters, and bold phase pi1n set could contain parameters. So here I am using the same kind of convention, but now basically what we have is bold phase pi1n sentences, not just bold phase pi1n formulas. So this is essentially this is this more formalized view of bold phase analytical hierarchy. Okay. So and of course we have truth definitions for these bold phase classes. So with this natural properties, so that it's so bold phase truth definition for class pi1n is itself is light phase pi1n formula, and so AC0 proves Tarski biconditional for this with second order parameters. Okay. So this is basically our language over which we'll do reflection. So now basically we could consider this ball-phase L2 series. Here, so in the course of this talk, it will be now to consider just the case when this ball-phase L2 series do have just countably many axioms. So in principle, one could go even further and consider this ball-phase series that do have uncountably many axioms. So basically, they, for example, are represented by some, I don't know, sigma one formula defining the set of the axioms or something like this. So it's possible, but it's not what we will do here. Okay. Yeah, and so now for this kind of series, we naturally have this Π1n reflection principles. So the reflection principles basically says that if ball-phase Π1n formula is provable in a theory, then it's true. Okay, sorry, ball-phase Π1n sentence. Yeah, and so basically when we're talking about ball-phase Π1n sentence, we already taken into account parameters. So it's more. So basically, what I'm saying here is more or less the same. If I would say formulate the schemata that would range over just Π1n formulas without any second-order parameters, just light phase schemata. But so I would then quantify all parameters and put them inside phi. So in substituting phi, and of course, the substitution of parameters will produce a ball-phase L2 sentence. So basically, it's the same thing. Okay.
So this will be the reflection schema, the second order kind of reflection you started with.
Yes. So basically, if you will say formulate something analogous to this, so basically, but here we will need these two kind of parameters. That it will be equivalent to the scheme that I wrote down below. So basically, so this essentially by going to this ball-phase L2 language is the way of substituting this stuff about this numerals that we have in first-order arithmetic. Okay, yeah. So of course, in first-order arithmetic, we could have done the same thing. So we could just quantify over all Πn sentences, and this would give us the equivalent form of reflection. Okay. Yeah. So now, of course, we could define iterations of reflection, but the important distinction here is that now we want not just to consider iteration over, say, elementary linear orders, or I don't know, primitive recursive linear orders, or something like this. So something kind of defined. But now rather we want to have iterations along arbitrary countable linear orders. So linear orders given by a set. So basically, if you have some countable linear orders, so subset of natural numbers. So basically, this some encoded linear ordering of a subset of naturals. So because we are working in the setting of second-order arithmetic, we basically need to so countable linear orders are this linear orders on defined as the subset of naturals that are given by a set. So now we will iterate our so Π1n reflection principles along this kind of linear orders. And yeah.
In this notation, in the first formula, the line above this one.
Yeah.
So this is the initial segment of.
Yeah. So basically,
yeah.
So this is just the initial segment of our order up to element A. Okay, basically. Okay, basically, this is a slight complication because because we kind of, so basically in secondary arithmetic we don't have ordinals, so we would do the same over set theory that already could talk about ordinals, that we would just he would say talk about iteration along ordinals, and then we could just talk about all smaller ordinals. But one should be
that will be the usual transfinite recursion or something like this.
Yeah.
This definition.
Yes.
So it's theoretic kind of transfinite recursion.
Yeah. But basically, what I'm saying is that in the secondary arithmetic we couldn't do this directly. So because those are linear orders rather than ordinals, and then okay, basically one should be careful about the things, and what I written is say a correct version, and of course, so basically if one don't want to be precise, one could just write, say, all betas less than alpha. It will be morally the same thing, but just one should be careful about what exactly does this mean. Yeah, and so here so more precisely here what this means is that so we have this, so given a linear order alpha, we could arithmetically define so relative to alpha this order linear order alpha restricted to all elements less than a. And this is what we are doing here. Okay. Okay, yeah. So basically, so here's this distinction. So I'm talking about two kinds of iterations. So iteration with R and iteration with RFN. And the difference is that iteration with R is theory, and iteration with RFN is a sentence. So basically, but the connection to follows, so that if you consider successor ordinals, so ordinals of the form alpha plus 1, then this alpha plus 1 theory is the same thing as T plus this alpha plus 1 iterated RFN. So basically, this is basically for successor. What's happening here is that for successor stages, so this theory Π1n R to alpha plus 1 is finally axiomatizable over T by this sentence Π1n RFN to alpha plus 1. But for limit ordinals alpha, okay, or say basically this, or in the terms of linear orders without the greatest element, this is not exactly the case, so one should be more careful. So basically for this for the limit ordinal, so the theory is not finitely axiomatizable, and so it's axiomatized by this all RFNs less than given alpha. Okay. Okay, so here, yeah. So I think I haven't mentioned the one important point is that actually this talk is based on my joint work with James Walsh. So I forgot to mention this in the beginning, but so I need to mention this now at least.
It was in the abstract of your talk. So
yes, it was, but maybe some people here didn't read the abstract, so then I still should mention that it's based on my work with James. Okay, so here is this first theorem that I want to mention. So this okay, so basically this is connection between iteration of Π11 refraction and Π11 ordinals in the more standard sense. So basically what's happening here, if theory T have the same Π11 consequences as alpha time iterated Π11 reflection, then the proof-theoretic ordinal of T is epsilon alpha. Actually, one thing about this is something that should be expected. So this, so this is basically this is a kind of this iteration of Π11 reflection. Basically, this weakest. So this is so basically this Π11 reflection is something very weak, and so then it's very natural to think that if we add to a same C, say to AC node this Π11 reflection, this kind of the smallest step that could be done over AC node. And so, of course, it's very easy to show that proof-theoretic ordinal of any theory extending AC naught is an epsilon number. So basically, because if you work in AC naught, we could show if alpha is ordinal, then omega to alpha is well ordered, and thus, so the suprema of order types of probably well ordered binary relation by necessity will be an epsilon number. So because it should be closed under omega maximization. So it's kind of expected that so this should be an so this iteration of Π12 reflection should correspond to just epsilon all the epsilon numbers. Okay, so this is okay, but basically this is from my older work in James. So now, but now so we want to build up on this and so consider stronger theories, not just this theories of iterated Π11 reflection. Okay, so now in order to get to stronger fragments of second-order arithmetic, we need to consider omega model reflection. So so of course, so basically in second-order arithmetic, we could talk about ordered omega models. So what is omega model? Omega model is just a model of second-order arithmetic where natural numbers are standard, and we only manipulate with this allowed set of natural numbers. So essentially, an omega model of second-order arithmetic is this family of sets of natural numbers that is the domain of sets within this model. Okay, and of course we could work with countable coded omega models in second-order arithmetic, basically because we could encode countable family of set of natural numbers by a single set of natural numbers, and thus this allows us to talk about omega models. Okay. And so here is this scheme of Π1n omega model reflection. Okay, so I before saying what this means, so I need to mention that actually here my notation differ from I think this more commonly used notation about this scheme of omega model reflection. Basically, my scheme is dual to this more standard version. But so I'm using this kind of notation because it kind of so aligned with the way how reflection principles are denoted in the study of reflection principles in first order arithmetic, and further this start the study of them in second order arithmetic. So this basically there's some misalignment here. Okay, but not so. So basically, so the scheme of Π1n omega model reflection says that if a Π1n sentence holds in all omega models of theory T, then it's true. Or more precisely, because so this our bold-faced Π1n sentence contains some set parameters, it only makes sense to consider whether they're true or not in omega models that do contain all the parameters of the formula. So in fact, so the scheme, so it's so basically here quantifier over models is restricted to the models such that they contain all the necessary parameters, or in other words, that this sentence phi lies in this fragment of both L2 restricted to model M. Okay, yeah, yeah, and so this is okay. So and so this omega model reflection dually could be rephrased as the following. So if phi was both a sigma 1n sentence and it was true, then there exists an countable coded omega model of T where phi holds. And basically, this is the usual, I think, the usual way of state omega model reflection. So basically, in this more usual notation, this what I call Π1n omega model reflection should correspond to sigma 1n omega model reflection. But basically, just a slight difference in terminology, but okay. Yeah. Yeah, so and of course usually they were not in the terms of this bold-faced L2 language, but rather with about this formulas with parameters, but it's just equivalent, so it doesn't really matter here. Okay. Yeah, so an important point is that Π12 omega model reflection is kind of the weakest form of omega model reflection. It's equivalent to all this in omega model reflection that might have seen weaker. That's something, I don't know, something like Π10 omega model reflection or Π11 omega model reflection. But in fact, it's all equivalent to just the sentence that any set is contained in omega model of theory T. So basically, that this omega models of T, they are cofinal in the universe of sets. And this already gives you Π1n, Π12 reflection. And of course, because this is essentially this, so basically in the same way we have defined iteration of usual Π1, not usual, we have defined the iteration of Π1n reflection. We could define the iteration of Π1n omega model reflection, and basically because it's behave in the same way, so it's just operator on theories, and so yeah, so it's there are no real difference between this and between omega model reflection and usual reflection in the sense of how it's stated. Okay. But in fact, so iterations of omega model reflections could be iteration of Π12 omega model reflection over AC naught could be restated in a very familiar way. So namely, so alpha plus 1 iteration of omega model reflection is equivalent to the axiom that for any set X there exists omega to alpha plus alpha's Turing jump of X. So basically, but basically, if one thing about it, it's a very intuitive fact because what we are saying here is that let's consider how it begins. So in this, so we begin just with AC0. So AC0 is equivalent to the fact that any set for every set that exists during its Turing jump. Then in the next level, so we say this one-time iterated omega model Π12 omega model reflection of AC naught states that every set so is contained in countably coded omega model of AC naught, but it's more or less the same thing as that every set is contained in for every set that there exists its omega Turing jump, because omega, so basically omega Turing jump is basically this is more or less the same as the smallest omega model of AC naught over a given set. But then when we then iterate this, so for every step we basically iterate the amount of Turing jumps by omega, and this gives us this correspondence. Okay. So this is the way how this iteration of Π12 reflection corresponds to this more known series of iterated Π01 comprehension, or this is existence of Turing jumps. Okay. Okay, so first idea is to iterate a reflection over all the well ordering at the same time. So basically, there was the reason why I needed this to define this iteration of second order reflection, not along this, say, just elementary well orderings, but rather along arbitrary countable linear orderings, precisely because as I wanted to formulate something like this. So basically, we have this axioms that say that for every alpha is well ordered, then Π1n reflection iterated alpha times. Okay, and the same for omega model reflection, of course. So now, in terms of this kind of reflection, it's, for example, very easy to formulate what ATR naught is. So ATR naught is just that on plus one time iteration of Π12 omega model reflection of AC naught. But basically, so if we go back, it's very easy to see why it's the case. So because alpha plus one time iteration of Π12 reflect omega model reflection of AC naught is just existence of this iterated Turing jump. And so basically, so for example, one one standard way to formulate a system ATR node is that it's ACA node plus for every alpha, for every value during alpha, there exists alpha during jump. Okay, one should be a bit careful about how exactly it's formulated, but basically it's that. And here, of course, so this is this when we consider this on plus one time iterated reflection, it precisely says that for every alpha we have this alpha time iterated omega model reflection, and this gives us omega to alpha during jump. But basically, it doesn't matter. In fact it's not stronger. So because this difference between when we say that for every alpha there exists alpha during jump and that for every alpha there exists omega to alpha during jump, actually it doesn't really matter because of course already AC node could prove that if alpha is larger than omega to alpha is larger, so it's just the same axiom. Okay, so we have this characterization of ATR node in terms of this 1 plus 1 time iterated reflection. Okay. So now the next next step is to analyze omega model reflection.
May I ask you a question about this formulation of ATR node?
Yeah.
So there was this recent work by Fernandez and Joosten where they
yes, right.
Some other
it's something. Yeah, right. So they had some very similar characterization. Yeah, I think there are some subtle differences that I couldn't recall exactly now, but yes, it was very close. Okay, there's some basically they okay, but so basically so I'm not exactly remember what they had, but yeah. So I think that so basically they had this kind of iteration along the all the countable well orderings. So they had this component. I'm not sure what they have exactly iterated Π12 omega model reflection, but so basically it was something very similar. I just couldn't remember the precise details.
Okay.
Yeah, but I think there was some slight difference. But basically, nonetheless, it's not main result of the today. So it's not like.
Of course, I just want. I thought that it was somewhat more complicated what they had. So
yeah. So the basically some slight. So basically, I think that what they didn't have was this boldface L2 language. So because of this, that somehow it was a bit more complicated, but because they need to consider this oracle probabilities. So, but I think it's more or less the same. But yes, okay. But, okay. Regardless. So. Yeah. But okay. So now we're getting to this main technical lemma, and so basically this is this kind of correspondence between omega model reflection and usual reflection, and in fact it's very simple. So namely, Π1n omega model reflection for Π1 n plus 1 axiomatizable series is the same as 1 plus 1 times iterated usual reflection for the same theory. So basically, omega model reflection is simply 1 plus 1 time iterated usual reflection. And basically, it's not like it's set. I think in this form it's new, but basically, it's just kind of similar to what we already known. Namely, So namely, there was this connection between omega model reflection and bi-induction. So by the scheme of Π1n bi-induction is simply the scheme that if you have some in second order that you have some ordering, then you could do induction for Π12 formulas of it. So it's important to note that, of course, so one could think of the smallest, say, why it's not obviously provable. So the point is that, of course, it's something provable, say, in full sector data. But when you work in weak system like AC node, so where we don't have a comprehension for Π12 formulas, and indeed we just have comprehension for arithmetical formulas. Actually, so so when we state that something is valid, essentially say that it doesn't have infinite descending arithmetically definable chains or arithmetically definable with set parameters. But here we want to do induction for more complicated formulas, and it's let's say it doesn't really fall from axiom of AC node that we could do this, and this is give us some proof-theoretic strengths. Okay, regardless, so basically we have the scheme of Π1n by induction, and it was so proved by Harvey Friedman that so this say full scheme of by induction is equivalent to full scheme of omega mod reflection, and this refinement by Stram and Hege. But so basically, so our because of course here we need this refined version in a sense. So of course, in this sense, what we'll do here will be more close to what Stram and Hege have done. And in a sense, it's I would say it's even more refined version of this result of Friedman. So because basically the point is that there is this one could show basically there is this connection between iteration of reflection along on +1 and by induction. But basically the point is so this so iteration of reflection they allow you so basically there are no so this so basically the already Π11 by induction corresponds to iteration Π13 reflection along the class of ordinals, and however yeah, so basically, so the weakest form of by induction you could consider is Π11 by induction. So all this actually, say Π10 by induction would be just equivalent to Π11 by induction. And this Π1 by induction actually corresponds to iteration of Π13 reflection along on +1. But this actually, but here actually we could consider this iteration of Π11 reflection. And Π12 reflection along the class of ordinals. This actually iteration of Π11 and Π12 reflection are equivalent, but the point is that basically we could go one level weaker, and actually it's meaningful. So it's weaker system. So say this basically we could apply the same idea to Π12 omega mod reflection rather than Π13 omega mod reflection that was possible with by induction. So in this sense, it's kind of refinement of what was done by Stram and Hege by one level below. Okay. Yeah, but basically this is the idea is more or less the same. It's just some adaptation corresponding to the fact that now we are talking about iteration of reflection rather than talking about by induction. Okay, so basically, basic idea of all this argument is the following: so that so if there are no omega model of something, so say theory T plus some true sentence or something like this, then there exists biformalized completeness of omega proofs. There exists an omega proof of the negation of the things that we want to have omega model of. So basically, so non-existence of omega models imply existence of a certain omega proof, and more precisely cut-free omega proof. And then basically what we want to do is we want say in our case we want to iterate reflection along the Kleene-Brouwer order of this omega proof. And then to prove this certain connection between this between partial iteration, so iteration along certain point or in our proof tree, and this the sequence in this point. So basically, want to show that from a bit theta. So it's the proof in the next slide. So basically, what we want to show is that so consider this. So suppose for contradiction that say on top plus time iteration of Π1n reflection fails, but Π1n omega mode reflection holds, then sorry, no, sorry, other way around, sorry. Right. Right. So we basically assume that Π1n omega mode reflection fails, but we still have this on plus one time iterated to usual reflection. Then we have this sigma 1 n true sentence, such that we don't have an omega model of this sigma 1 n true sentence. This gives us an omega proof. And basically, then we iterate reflection along clean brow order of this proof. And basically, then it's possible to show that so basically by that iteration for up to certain point in this clean brow order gives us implies the truth of the this sequence in the corresponding node. And so this in that iteration along the whole order gives us this should imply this formula not phi that should be in this end of our proof, but not formula not phi should be false, because by assumption phi was true, and this gives us a contradiction. But basically like this. So okay, the main point is that we iterate reflection along clean brow order. Okay. Okay, so basically this is our main technical lemma. So this is that connects omega mode reflection with iteration of usual reflection. And so in a sense, it's a kind of Schmerl formula, but it's with order one because it's not for series, but it's not for conservation result. It's so it's just equality. So we say kind of just reduce omega mode reflection to this iteration along this class of ordinals. Okay. But essentially, the point is we are actually using this result in a similar way as a Schmerl formula. So it's, okay, so then, okay, so basically this analysis by this establishment of Schmerl formula in the setting first arithmetic actually required some conservation results, and we will need conservation results as well. So namely, so we have the following conservation results. So first of all, this is a direct analog of what we had in the setting of first order arithmetic. So basically, here, if we consider the so this Π1n plus 1 reflection over theory U, is that this theory is Π1n conservative over T plus this Π1n reflection rule. Actually, it's a bit complete. So it's a bit. One need to be careful when formally. So when defining what exactly does this thing mean. So because here, so in the setting of first order arithmetic, of course, we talked about this just countable series, and here we're talking about the series in this uncountable language. It's a bit complicated things, but I don't want to go into this formal details. Basically, the point is that they could be formulated. And so we have this direct analog of this conservation result. So let me remind, in the case of first order arithmetic, the result was that pi n plus 1 reflection is conservative over the closure of the theory over this pi n reflection rule. And so we have the same thing for omega model reflection. So now, of course, pi 1 n plus 1 omega model reflection corresponds to pi 1 n omega reflection rule.
And so where are the complications here?
No, okay, it's not, it's like not real complication, but basically one need to begin the complication with how to formulate this. So because here we're talking about this rule in class size language.
Yes.
Okay, but okay, basically it's not. I don't think it's a real difficulty. I think it's more. It's very similar. See, the idea here is very simple one, but
still it's the same rule. From one sentence we infer.
Yes.
One sentence.
Right, but basically he was here. No, yeah, sure. Yeah. I mean, it's not the truth, but the point is that we want to formulate this result over AC naught, and this is this class size language. So
yes, so it's really one should be careful how to formalize it.
Yes, right. What really does? What really are the deductions in class size language? There's a lot of subtle problems here. One should be careful about. So, but basically, I don't want to go in this direction right now. Basically, I don't think that this kind of technical difficulties are that interesting in the end. So, okay, so basically, because everything works as one would expect it to work, but one should be careful about the definition. Basically, that's just like this. So. Okay. 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 Yeah. And so basically, then this allows us to obtain the following Schmerl formula. Okay. Oh. Yeah. Sorry. Oh, there's some typos. Sorry. Okay. So basically, this formula should say the following. They should say that. So the important part is that that we have direct analogs of the formulas for first order arithmetic. So let me show them again. Okay, yeah. So here is this formula for first order arithmetic, and that you could trade off the levels of arithmetical hierarchy with omega exponentiations in reflection, iterations of reflection. And here actually we have exactly the same. So now we're trading of the levels of analytical hierarchy with again omega exponentiations. So actually it's just the same thing. So it's more to do with this crisp. So amount of levels. So somehow it's all of this is not really reflected in some kind of further proof-theoretic extents. But okay, regardless. So basically here we have the same kind of trade-off. But so what I wanted to say is that so basically we are doing so this is done over the assumption of all true sigma 1-1 sentences. So it's yeah. So I think there's some typo. So basically, so in all these formulas, what I actually wanted is to add all true sigma 1-1 sentences to the both sides of the equations and have pi 1n conservations. Okay. So and so.
Upper index should not be there.
So in some version slide I use this upper index, but I decided to move to different types. But yeah, so I somehow haven't done properly. Okay, regardless. So yeah. So and basically the point is that it could be done for omega model reflection itself. So basically, what it's saying that Schmerl formula is really nothing to do with the fact that Schmerl consider first order arithmetic. It's more to do with just this say structure of so if you just have this reflection principle for various levels of some hierarchy there, and we have this necessary conservation results. Basically, we just obtain this Schmerl formula. So it's kind of much more universal fact than just the fact about first order arithmetic. And of course, it's again not I guess not that much. new because, for example, if so there is this analysis of say system ACA, so basically some various system of second order arithmetic with a full induction schemata, and of course full induction schemata corresponds to the full schemata of so full uniform reflection for all pi for the for classes pi1n. And basically, so this analysis is just showing that is done by relativization of Janssen. So basically, that the same analysis that was done in the case of PA could be done relative to this systems of second order arithmetic, and so arithmetical induction just corresponds to this transfinite induction up to epsilon naught, but by form less complicated formulas. And basically, this is just all of this is just a kind of reflection of the same fact. Okay. Yeah. Okay, so and now, so the last thing that we need to deal with is those iteration along the class of ordinals. And here, and basically it works like this. So this on plus one time iterated reflection is pi1 conservative over iterated reflection rule. So if alpha is well ordering, that you could iterate a reflection along alpha. Of course, it does. The point is that it doesn't work all complexity levels. It's basically it's due to it's only working for pi1-2 reflection, and in fact, in principle, as a for pi1-1 reflection, but it doesn't really matter. Yeah. And okay, basically, it's due to the fact that say the notion to be overloading is pi1-1 complete. And because of this, we could have this power conservation for pi1-1 formula, but we wouldn't be able to do it in the next complexity level because notion to be overloading is not pi1-2 complete, and basically this that would break this kind of construction. So this basically this style of conservation only possible for this pi1-1 level. Okay. Yeah. So, but what important to note, it doesn't that much matter because as we have seen before, so we could so we have its conservation that allows us to reduce pi1-2, say pi1n omega mode reflection to this to pi1-2 omega mode reflection. So because we have the Schmeral formula for it, and next we could apply this style of conservation for pi1-2 reflection. So. Basically, this still is very powerful tool. Okay, so so finally, so what I want to do is to apply this kind of conservation results to ordinal analysis of this series defined in terms of iterations of the second order reflection principles that I have considered before. Okay. And here we will have this important technical notion, namely the notion of proof-theoretic delators. Okay, so basically, I don't really want to go into explanation of what delators are in general. The point is that delators are this certain kind of functions from ordinal to ordinals that really are, say, behave very nicely and could be in fact applied just to arbitrary even linear orders, but and so in the case when they apply to well orders, they should produce well orders. So basically, this kind of, in certain sense, there is this kind of operators on linear orders that preserve well orders. Okay. So because I don't want to go into technical definitions, so this is what we need, all we need to know about the latest now. But yeah. But the point but for people that are aware about this, the latest stuff, so it's basically everything that I will talk about so about today in the setting are the latest. Okay. Yeah, so okay, again, so we have this usual definition of Π11 proof-theoretic ordinal, so just supreme of order type of yeah, wait a second. No, okay. Oh yeah, right. Sorry. Yeah. So actually here so the usual definition of proof-theoretic proof-theoretic Π11 proof-theoretic ordinal is a supreme of order type of, say, primitive recursive linear order such that theory proves that they are well ordered. But now we're actually living in this relativized setting. So we have this theories with set parameters and so on. Because of this, actually, we want to quantify not just over, say, primitive recursive linear ordering, but over arbitrary delta 0, 1 linear order. So both phase delta 0, 1. So basically, you want to have this linear orders with set parameters. It's actually more the same. It considers the set encoded linear orders. And now, so basically, so we want to look at all these linear orders with parameters such that this theory proves that they are well ordered. Actually, and so this gives us this proof-theoretic ordinal. In fact, one could it's quite easy to show that for theories in just usual second-order language, so without parameters, actually this notion will coincide. So we will not somehow get to larger ordinals by considering this definition. But of course, so basically, if you have some theories that have some useful useful axioms about with set parameters, for example, if you can, for example, consider some say I don't know, some ordering of the order type omega-1 Church-Kleene. So basically, we have this set constant, and we could, of course, so theory without parameters wouldn't be able to prove that this set is well ordered. So it's not possible. However, so we could have just externally add this kind of axioms. So say, for example, this particular say well ordering with the order type omega-1 Church-Kleene is well ordered. Okay, basically, the part of this axiom is just that this linear order x is well ordered, but externally we could x could be, say, could have, for example, type omega-1 Church-Kleene on some other large non-recursive ordinal. And then, of course, this proof-theoretic ordinal of theory with this kind of axiom by necessity will be above omega-1 Church-Kleene. So this is kind of, basically, this definition allows us to go beyond omega-1 Church-Kleene for system with parameters. Okay. And now, so then we could consider this theories as this operators on ordinals. So basically, for given linear, so we basically for given linear order alpha, we always could consider the theory T plus alpha is well ordered. And the point is that and this gives us certain and basically the system was Π12 sound theory T that we consider was Π12 sound. This gives us certain function from ordinals to ordinals. From countable ordinals to countable ordinals. And so so basically we want to characterize this function. And in fact, in all our cases, this will be a delta. What I haven't told what the latest what the latest are. So for people who don't know, we're just giving some reasonably nice definition of functions from ordinals to ordinals. Okay. So basically, so I'll need the following functions, and so basically, of course, so here in fact they should work as functions from linear orders to linear orders. So because despite this say extensionally a particular, so it's function from order to order, so the relevant situation is when they apply them to velour rings. But in principle, so we actually want these operators to work just on arbitrary linear orders. Basically, so we have this. We want to have the following operator. So we want to have operator epsilon plus. So this operator basically maps a given. So should map a given velour ring, the velour ring with the order type of the next epsilon number above the order type of this velour ring. And basically, what this means is that we consider this relativized notation system. So where we have this counter normal forms. And basically, it's quite easy to make this, to give the systems that will have this necessary order type. Basically, so we have this, so system with counter normal forms. Else, so we have this notation system for for Veblen functions. So we have this operators phi beta plus. So let me recall that the phi beta is beta's Veblen function, and this plus mean that we consider this. Yeah, so the next, so basically, so this epsilon numbers versus values of function phi1. So so basically, so the ordinals that versus fixed point of operation omega maps to omega. Sorry, to the of the operation omega to x. And so this is of course further generalized, but by more powerful Veblen functions. So this phi2 enumerates fixed points of function phi1, phi3 enumerates fixed points of phi2, and so on. Yeah, and basically, so phi2 plus is maps to the next value of function phi beta, or if in the case of beta was something like gamma plus 1, this should be the next fixed. So this is maps alpha to the nearest fixed point of phi gamma that is above alpha. And again, it's possible to define a notation system that does this. And finally, we have this so function gamma plus, then again maps alpha to the next gamma number again. And so and basically this for people that okay, so basically these gamma numbers are these numbers that are so it's ordinal alpha is called gamma number if so ordinal alpha, so for any beta less than alpha, phi beta of beta is still less than alpha. So it's kind of close under this arbitrary Veblen functions with indices below it. The value of this ordinal. Okay, and so the important point, important question that so the proof-theoretic ordinal of ATR0 is actually number gamma 0. So this first gamma number. Okay, but here we actually are able to characterize this, say, various standard systems as operators or so on ordinals, and so this. So AC0, it actually, not surprisingly, corresponds to the operator epsilon plus. Okay, so actually it's basically it could be done by standard techniques, and in fact, so we kind of so our analysis starts with this as a starting point. So basically we don't do it by some reflection-based analysis, but rather we just use this fact. But basically just a variation on the standard analysis of AC0 plus a statement that something is velour-red. Okay, so basically AC0 is this corresponds to this epsilon plus, then say AC0 plus. So AC0 plus is of course the system AC0 plus axiom that states that every set is contained in countably coded omega model of AC naught. Actually, it corresponds to the function phi2 plus. And ATR naught, so it corresponds to gamma plus. Okay, and basically, so how we have done it? So basically, we use this kind of conservation results that I talked about before in order to calculate operators corresponding to various systems in of the relevant form. Okay, so here we need even more general notion or more general operator. So namely, we have this operator phi beta plus gamma of alpha. Okay, it may look a bit odd, but basically what this is the following: is that so we have this ordinal notation system for gammas ordinal above alpha that is a value of phi beta. Okay. Yeah, so basically we are going from alpha, but not just to the nearest value of phi beta, but to this gammas value of phi beta. Okay. Yeah. And here basically what happens is that we so iterations of pi12 reflection increase so over a theory for which we already knew this it's proof-theoretic delayed to be phi alpha plus, it should be corresponding to this. So basically beta times iteration corresponding to this omega to beta time iteration of this delta. So basically like this. And yeah, and so it's actually fairly easy to show. Then the previous fact could be applied to system of omega model reflection. Basically, because of omega model reflection, we have this characterization of omega model reflection as on plus one time iteration of usual reflection, and we could then we have this conservation result for on plus one time iteration of usual reflection as this iterated reflection rule. So basically, so for from omega model reflection we go to theory like this. So with on plus 10 time iteration of pi12 reflection, and then itself we could then characterize pi11 consequences in terms of this iterated pi11 reflection rule. Yeah, and so. And basically, this conservation result allows us to apply this first line of the SLAM method to obtain the second line. And finally, by iterating this second line, we could obtain third line, so that characterizes iteration of omega model reflection. Yeah, and so this gives us so this iteration that alpha time iteration of omega model reflection is this operator of phi plus of 1 plus alpha. Yeah, and basically, so then applying this characterization, we could see that, say, ATR naught is equivalent to, say, something like that. If alpha is well ordered, then phi alpha of 0 is well ordered. So basically, because so as I already mentioned, so ATR naught is actually axiomatized by the sentence that says that if alpha is well ordered, then we have alpha time iteration of pi12 omega model reflection for AC naught. And in the previous slide, we have this characterization of iteration of pi12 omega model reflection of AC naught in terms of this operator phi alpha plus. And basically, it's from this, it's very easy to go to this well ordering principle, so that if alpha is well ordered, that phi alpha of 0 is well ordered. And so we could do the same for, say, for AC naught. Oh, okay. Yeah, so I actually have even some proof, but basically it's more or less what I have said. Yeah.
So this, the first of these results, I think, was known from some.
Yeah. It's yes, right. Yeah, sorry. I mentioned, just yes, right. So just reproving this quite known results. So it's So I think it's who actually was the authors. It's So there was several papers on this. So maybe Andres, do you remember it better if he's still here? No, I think we don't have Andres anymore. Yes, I think it was a result by Andres, Harvey Friedman. I think maybe so. Okay, I don't exactly remember the authors, but so.
Anyway, this was. So it was.
So it was. It was known. Yes. So indeed not new. Okay. So we have this. Characterization. Well, basically, so what I'm saying is, so in addition to this, so basically this analysis of iterated reflection actually allows us to obtain this characterization of this standard system of second order reasoning by well-ordering principles that we actually already known, but but nonetheless. And so in fact, so I think basically the same technique could give characterization for even slightly stronger systems. So namely, so of course this is it seems that it's really possible to apply this technique to series that are given by something like Π13 omega modular reflection, and this basically so allows us to go to the level of something like Π12 by induction, and so this will go so lead to the systems that are slightly stronger than ATR naught, and so but it's still a work in progress. Okay, so and so else in the same time we could of course apply this to calculate proof-theoretic ordinal, because so if we characterize this proof-theoretic delator of the system, we already know it's proof-theoretic ordinal, because basically when we apply this delator to the ordinal 0. So empty assumption, and this gives us this proof-theoretic ordinal. And so here we have this again, the standard facts. Nothing new should happen here. Okay, so okay, basically that's all.
Okay, thank you. Very interesting. So, do we have questions? Then we will thank the speaker. Maybe now everyone is showing reaction. Let us show that too. Okay, so there were plenty of new results, and I think most interesting here was that somehow this Schmerl's idea in this second order setting has a great clarifying effect on relationships between various systems. Right?
Yes. I say I think it's perhaps it haven't been realized this before this. But somehow it's happened to be that so Schmerl formula is much more general, and I think it's in retrospect it's very similar to this relativized Gensen ordinal analysis. So basically, so people already have done this, but I think not for Schmerl formula. But basically, so this was essentially a combination of two ideas. So this is the fact that we could, so this Schmerl formula works for not just for standard reflection principles, but for all kinds of reflection principles. The first observation, and the second observation is that we could so use this Friedman style so correspondence between omega modular reflection and by induction for iterated reflection. And basically by combining these two facts.
So this equivalence between the iterations on +1 iteration of
Yes.
phi1 and reflected. Well, that was the central kind of technical claim. Seems to be from it everything more or less plus relativization of Schmel, that should give you the more or less this all results.
Yeah, basically like that. Yes.
Now, there are several questions one can ask here. For example, the first one is this idea of proof-theoretic delator. Right. I see the somehow. So this seems nice, especially because it's rather clear that you arrived to it by this analogy with the delator work that you did before. And here you sort of get these operators from the material that you already have in this
yes. So basically,
series, which is
yeah. So what I could comment this is that basically, so this, of course, so the people before considered this equivalence between say systems of second order arithmetic and so well ordering principle. So basically, the statement that so say ATR naught is equivalent to the fact that this Veblen delator is a delator, right? So this is kind of, but actually, it's this kind of results are not fine enough for the kind of applications that we needed here. So basically, it's so notion proceeding delator is something extremely close to this, but in fact, I would say it's a slightly better notion, because in the sense that so we could easily recover this kind of say results about well ordering principles from our notion of proof-theoretic delator. However, so when we're proving this, so basically certain results about analysis of system second order arithmetic by induction, in fact, this is the right assumption about proof-theoretic delator is the right assumption, and so the assumption about say equivalent well ordering principle. Maybe it's possible to do make it work, but it's not clear how to do it. But so it seems to be more, say, a better technical notion in this setting.
But could you show the slide where you had this this result about reduction of pi1 to omega model reflection to this rule with from the well ordering of something?
Sure.
So that one. Yes, so it seems to me that this notion of delator that you have here is essentially emerges by something like analysis of such a rule, right? So you basically have so you add to your series a well ordering axiom, and you see what you will get at the next step. So
yes, kind of
one application of such a rule, you will get this.
Basically
well ordering that you will be able to put. So that's essentially the analysis of this autonomous iteration.
Yes, kind of. Basically, because so if you think about this, basically what we have here is the following. So in the previous level, basically in the previous level, we had some delator corresponding to function phi alpha, right? And then so we want to go to the next level of iteration for omega model reflection. And what happens there is how we have this rule that so connects iterated omega model. So with omega model reflection, we with this so basically connection using this omega model reflection, this rule. And basically what this does is that you make this your closure under this previous so basically you go from enumerating facts, so going to the next value of phi alpha to going to the next value of phi alpha plus 1, because so if you look at how Veblen functions are defined as basically, so it's next Veblen function is this enumeration of a fixed point of the previous one, and so basically if one look at this, it's basically what's happening here. So it's more. Yeah.
Okay. Good. There is a question from Zhenya Kolmakov in chat.
Let me see. Okay, slide 11. Okay.
By the way, it would be nice if your slides will be sent to me. We will put them online.
Okay, yeah. I think I will need to fix a few typos, but yeah, okay.
Here, corollary probably.
Okay, right. So yn plus 2. Yeah. So it's a very easy. The point is that okay. So the question is about this. First lemma in the slide. So and about this second equation. So y condition is that the n is greater or equal to 2. Okay, so and not to 1, and so it's very simple. The point is that yeah, so basically Π11 omega mode reflection doesn't really make sense, and it's the same thing as Π12 omega mode reflection. Yeah, and so because of this, so it's this basically wouldn't work, and so the point is that Π1. So basically, this the proofs of this fast rely on the complexity of axioms. And what's important here is that say Π1. So this Π1n plus 1 reflection is complexity Π1n plus 1, and Π1n reflection has complexity Π1n. Okay, here, but when we go here, what's happening here is that. Okay, so basically, say Π12 omega mode reflection has complexity Π12, Π13 omega mode reflection has complexity Π13, and so on. However, Π11 omega mode reflection is the same thing as Π12 omega mode reflection. It has the complexity Π12, and because of this, basically this construction fails if n equal to 1.
But n equal to 1 means Π12 reflection rather than Π11 reflection.
Okay, yeah. So no, n equal to 1 should have meant the following. So it should have meant that Π12 omega mode reflection is conservative of the closure of Π11 omega reflection rule. But actually, this is completely false because first of all, so Π12 omega mode reflection is the same thing as Π11 omega mode reflection. So this would mean, but basically, very clearly that the theory to the right would be stronger. And so I'm explaining now why the argument wouldn't work. And this is the reason is that argument relies on the complexity of axioms. And the point is that so basically this Π11 omega mode reflection have complexity Π12 as Π11, which would be analog in all other cases, and thus it doesn't work. Yeah, basically like this.
Okay, good. Okay. So, do you have any text in any?
Unfortunately, not yet. No. But we should prepare it.
Okay. Final question. So, if you consider this model operators corresponding to omega model reflection.
Okay, sure. Yeah, right. Yeah, sure.
And ordinary. So, what you will do?
You want basically some kind of reflection calculus.
Yes.
Oh, yeah, sure. I mean, right. Yeah, I actually don't know the answer, but this shouldn't be that hard to figure out. Okay, at least okay, depends. So basically, what we have here is that we have this kind of two operators of say on the same complexity level. So in the usual reflection class, we have this say we just have Π1 reflection, Π2 reflection, Π3 reflection, and so on. Basically, we have this goes by complexity level, and here basically we still have just one Π1 reflection. Yeah, But essentially, this on the second level, yeah. So we have basically two reflections. We have this usual reflection and this Omega model. But basically, if you think about Omega model reflection, this on plus one time iteration of the usual reflection, I think you should basically very much suggest you that basically you have this kind of basically I think it should work more. So you just consider this reflection calculus with this operator. Basically, I think you could just think about this as just a long iteration of this. So replace Omega model reflection by iteration of non-Omega model reflection along long enough ordering. So, for example, I think epsilon 0 should be enough. in the level of reflection calculus. I don't know what the logic is, but basically I think so.
Anyway, you think that you can sort of
but here
do it to the level that it will match the results that you have.
So it depends what exactly you are asking. So if you're asking whether it's so, what is the reflection? So I was answering the question, what is the reflection calculus?
That is a question that might be that's probably an easy question. So what is the logic of these? That's surely can be calculated. I believe that's
yes, basically.
Although that's a problem, it's looks like everything is the understanding of these operators is enough to characterize it. And the other one would be to have it together with the appropriate reduction formula.
Right. But but here again, so here the different question, because I think the right calculus for this case basically should be the calculus where we have this alpha time iteration. So basically, if you look at what happened here, what we really need is this kind of relativization of reflection calculus to ordinal. So basically, we need this kind of ordinal parameters in reflection calculus, and then it will kind of make sense. And basically, if you do it without parameters, it definitely wouldn't work, because it's not what is going on here. And basically, you will not have this reduction properties in the reflection calculus. Then I think it could be done basically. But basically, so what will be there is that you will have this iteration of reflection along ordinals alpha, and then you have this Omega model reflection correspond to this iteration along the class of all ordinals, and then I guess it wouldn't be that difficult to say make all the necessary reduction, prove all the necessary reduction properties and so on.
Okay, good. Any remarks or further questions to further? So we are probably already rather late by now. So but that's okay. So thank you for the very interesting talk.
Okay, thank you for inviting me. So I think maybe my talk was a bit too technical. I'm not sure what everyone managed to follow, but okay.
I think some people at this seminar were able to follow you. So that's for one thing. Of course, it was dense. I mean, as a general, don't give such talks, at general conferences.
No, I mean, of course, yes.
But okay. It was quite informative.
Okay, okay, good.
Bye-bye.
Bye-bye.
Thank you. До свидания всем. Ну и на следующей неделе у нас доклад Степана Кузнецова. Вот. А что будет дальше, мы там, как говорится, договоримся. Есть несколько хороших спикеров, но с неназначенной датой, так сказать, пока что.
Небольшое добавление к Львиной последней ремарке, что И больше такой доклад не делайте. Вспоминается бессмертный диалог Штирлица с Мюллером, когда Мюллер сказал: никому не доверяй. Мне можно. Вот мне это нашему семинару.
Нет, ну нормально. Нет, ну, как говорится, тут все свои, поэтому, как говорится, да. Немножко жестко было бы для, так сказать.
Пошел такой вот самое, поможет вашему английскому, если вы запомните, что линейный в английском не linear, а linear.
Я так говорю?
Как прилагательное это linear. Это сразу уберет у тебя, то есть у вас около 20-30 режущих слуг.
Хорошо.
Просто как, если запомнится, но не запомнится.
Ну да. Еще есть variables и variables, так сказать, такой.
Да.
Variables, variables.
Шаг за шагом. Всего, так сказать. Я надеюсь, что мы...
Федя не говорил variables, это надо сказать.
Я думаю, что Федю мы будем продолжать слушать и так потихонечку давать, как говорят, старческие советы по мелочам. Ну ладно. Все, счастливо. Спасибо, Федя, замечательно все.
Да, всего доброго.